VLSos here. This is a video lesson on curve analysis. And by curve we mean function, and by analysis we mean finding the location of features of a function and justifying and labeling what kind of features there are and where they are. I've prepared a piecewise function to analyze, and I've made a list of the various things that can be said about a function, and we'll find if we can say them in this function here. The letters locate specific areas of the function so that we can reference where this behavior might be. Top of the list, zeros and intercepts. This doesn't require calculus. We would look for zeros where it crosses the axes. Horizontal axis is crossed at A and C and J. So we would have zeros or x-intercepts at A, C, and J. Not just the horizontal intercepts, but we have one, this vertical intercept, would be found where we put, if we called this the f function, where we put 0 in for f. We spend a lot of time in our beginning algebra classes learning how to find intercepts of graphs and equations. Extrema are those locations of extreme value. Extrema is generic for any place that is a maximum or a minimum. And it could be a maximum over the entire function, or it could be a maximum in a specific local area or region or piece of the function. For example, at I, we have a maximum. It's a highest value amongst the values around it, but it's not the overall maximum. It appears that we have a maximum at E, which is higher than the one at I. But there is a maximum both at E and I. G is another extremum called a minimum because it is the lowest value amongst the values around it. So finding extrema in this function, we would be able to say that there appears to be extrema at E, G, and I. These are values. Notice that there is a horizontal asymptote, and the behavior of the function as we approach the asymptote from both sides is that the function appears to go to negative infinity. We wouldn't say that negative infinity is an extrema because it's a value that cannot be reached. So we don't include the concept of infinity for maximums and minimums. And indeed, the value at G is not lower than the values that are approached here by the function continually going down to negative infinity. G is a minimum, but only amongst the points around it. Intervals of increase and decrease, where the function is headed down, it's decreasing. Where the function is headed up, it's increasing. A function will be increasing wherever its derivative is positive. We can visualize tangent lines to the curve in many places. Every location where the tangent line is negative, like from negative infinity all the way up to B, highlighted by this curve here, which is going down, is an interval of decrease. So we could say the function is decreasing on the interval from negative infinity all the way up to, but not including B, where there's a horizontal asymptote. The function also decreases between E and G. Again, visualizing tangent lines, all those tangent lines would have a negative slope. So the function is decreasing on the interval from E to G. It's also decreasing from I and then everywhere afterwards, or on the interval from I to infinity. Where's the function increasing? Where is it heading up? Where could we draw tangent lines whose slopes are positive? Well, from B to E, we have positive tangent line slopes. The function is increasing. Increasing on the interval from B to E. The function is also increasing from g to h and from h to I. There's a discontinuity at h, so we're going to split up those intervals and list them separately. Intervals of increase and decrease. Intervals of concavity. Function could be concave up, concave down, or not have concavity. Visually, we see where a concave up region is a region that is like an umbrella curved downwards. A region where a function is concave up is like a bowl pointed upwards. In this case, from negative infinity all the way to this asymptote b, we have a curve that is concave down. And afterwards, from b to through e all the way up to f, we also have a concave down curve. Abbreviated CCD, the function is concave down from negative infinity up to this discontinuity at b, and after the discontinuity from b to f. The function is concave up like a bowl that could collect rain from f to h. We can abbreviate that concave up CCU on the interval from f to h. These pieces, which appear to be linear, do not have concavity. When we use calculus to justify where a function is concave up and concave down, we look to the sign of the second derivative. If we had the function, we would take the derivative twice. Where the derivative was positive, it would be concave up. So we would expect a second derivative of this function to be positive on the interval from f to h. Where a second derivative of a function is negative, it will be concave down. So why is there not concavity on these linear pieces? Well, they don't look curved. They're not, they're straight. But what happens if we were to take the second derivative at a linear piece? The derivative, the first derivative of a line, is constant. Think of the rate of change of this linear piece. The rate of change of any linear piece is constant, and if we were then to take the next derivative, the derivative of a constant would be 0. The second derivative of these two linear pieces is 0. It's not positive, so it can't be concave up, and it's not negative, so it can't be concave down. It doesn't have concavity here or here. An inflection point is a place where the concavity changes from positive to negative or from negative to positive. We have an inflection at f because we've shown that we have negative concavity up to f and then positive concavity afterwards. A change in concavity from one sign to the other is an inflection point. Changing from positive concavity to no concavity is not an inflection. It has to change sign, not go from one side to nothing. We have asymptotes and discontinuities. This doesn't take calculus necessarily to justify. We can see in the graph that we have a horizontal asymptote at b, and we have a discontinuity at h. Specifically, there is no absolute limit. Corners are fairly uncommon. The corner is a place where it is not linearizable. We could zoom in at this point at I and observe that there is a sharp, non-linearizable location. There will not be a derivative at I, as we will see how to justify in the future. We have a corner at I. And the end behavior of a function is what its infinite limits are doing. So this graph suggests that as x goes to negative infinity, the values go to infinity, and as x goes to positive infinity, the values keep going down to negative infinity. This is the language behind various features of a function and a little bit about how to justify them. Formal justification for these behaviors can be quite rigorous, and for most of them require calculus techniques. Those will be subjects or topics in future lessons.